Hello everybody, and welcome to an extra lecture segment for 6838. In this little video, I thought I would tell you about some of the realities of how to engineer an algorithm for mapping between surfaces that extracts a map that is really highly detailed, I guess, or really works at the finest resolution of a triangle mesh. In particular, I thought I would cover a little bit about one of the research papers that I had the pleasure to be involved with just a couple years ago. I should be really careful here to give all the credit for the hard work and the interesting ideas to Danielle Zeus, who was a graduate student at the Technion at the time. She's moved on. But this is basically just an example of a method for dense correspondence from one surface to another that, in this case, is just trying to optimize the distortion of a map. Now, the state-of-the-art changes when it comes to solving this problem just about every year, and no doubt by the time you all are viewing this video, the state-of-the-art will have changed at least 2 or 3 more times. But I think many of the big ideas in this research paper are sort of exemplary of the types of challenges we tend to face in the area of correspondence. And moreover, you get to just learn a little bit about the details of one top-performing technique. So in any event, if you want to get more information about this particular algorithm or to understand the details, you can take a look at this research paper. It was published in ACM Transactions on Graphics a couple years back, and I believe the code is online. Danielle also worked on some extensions of this algorithm that improve it even more, including one that I think was published at Eurographics, but I'm happy to send a link out to the course if you're interested. So this is an algorithm whose input, just like in our previous lecture, is basically a pair of triangle meshes. But the idea here, unlike, I don't know, maybe functional maps would be on the opposite end of some spectrum or another, the big idea here is to get a map that is low distortion and smooth at the vertex level of a triangle mesh. So you really want a high resolution mapping for one object into another. Now, in this particular application, for example, in computer graphics, we're going to be okay with maybe clicking a few landmark points so that we have some initial guess for the correspondence. And then the algorithm's job here is to fill in the dense correspondence everywhere else. This is different than, for example, some machine learning techniques that maybe need to process a big data set of shapes and can't afford to have somebody click corresponding points on every pair of surfaces. Here, we're more concerned with getting a high accuracy map, and we're okay with a little bit of user guidance. So I thought I would sketch out this algorithm just to give you an idea of how difficult this problem is and how tricky it is to get it right. Because there are a lot of aspects of this algorithm that are actually quite tricky, and were things that we really didn't anticipate when we started working on this problem. So I'll give you a bit of a high-level overview of the approach, and then we'll dive into a few of the details. Here, the basic input to this algorithm is a pair of triangle meshes. In Danielle's notation, we call them M1 and M2. And moreover, somebody has clicked a few sparse correspondences that we expect to be mapped to one another. And those here are denoted by the colored points. So here somebody has manually marked that the colored points should be mapped to each other, or at least nearby, in a desirable output for your mapping algorithm. And this technique is going to be basically an optimization algorithm, where it's going to start with some initial guess of what the mapping from M1 to M2, or in this case, I guess, maybe M2 to M1, should be, and then it's going to iteratively improve it. And so the original initial guess of a mapping here is going to be kind of brain dead, where what it's going to do is, for each colored point, it's going to take the Voronoi cell around that colored point and map that entire cell to a constant. So this is a really, really bad map between surfaces. Hopefully you see that. Essentially, that map is perfect, right, at the constrained points, of course, because somebody's clicked them. But then the map just doesn't change as I slide along the surface in some neighborhood of those landmark points until I reach the boundary of the Voronoi cell, in which case the map has a discontinuity and flips somewhere else. So this is just a really, really bad initial guess. And then what the algorithm is going to do is to iteratively improve this mapping until it converges on something low distortion and smooth looking. And the way that we're going to do this is to optimize an objective function, or an energy, which promotes the smoothness of the map and also the bijectivity of the map. So in other words, we don't want the smoothest possible map, in some sense, is the one that takes all of one surface and maps it to a single point on the other, right? That's a very smooth map. but the distortion and bijectivity is quite high. or rather, that map is not bijective, and it is high distortion. So we're going to add objective terms to that basic setup to avoid these sort of trivial cases and keep me in the class of maps that are interesting topologically. So the inspiration for our approach, which turned out to be a bit mathematically not well informed, and I'll tell you why in a minute, was to optimize an energy that we've actually already seen in 6838. That's something called the Dirichlet energy, which is what you see on the slide here. So if I have a mapping from surface 1 to surface 2, then the Dirichlet energy of the mapping from surface 1 to surface 2 is given by the integral that you see on the slide here. So basically, what I'm going to do is compute the Jacobian of the mapping, like d phi. This is just like locally, the sort of locally linear approximation of that map. Take the norm of that Jacobian matrix and then integrate it over M1. Now, the intuition here, which we've already applied to parametrization and a few other variational problems, is basically that a low distortion map is one for which the derivative is not so big, right? That's sort of what the Dirichlet energy is trying to capture. Notice that it's not asking that the Jacobian is close to a rotation, which would be a rigid map. This just wants it to be close to 0. So the smoothest possible map with respect to Dirichlet energy is a constant. And that's why we're going to need to add some additional terms that avoid that sort of trivial solution. Now, the reason that we studied this Dirichlet energy with Danielle and Miri was that essentially this is the standard objective that many, many algorithms use for one specific mapping problem, which is to take a surface and map it into the plane, right, in this parametrization problem. Here, rather than parameterizing into the plane, we wanted to optimize the Dirichlet energy of a mapping from one surface into another surface. But we're going to see that some problems arise when we do that. In fact, optimizing this energy over the space of maps, even in just some fixed homotopy class, turns out to be a bit of a not well-defined problem when the target of the map, M2, has a positive curvature. This is a subtle point, although probably for the physicists that watch this, they actually knew this in common knowledge. This was news to me. But ignoring that for now, our high-level approach here is pretty straightforward. So that Dirichlet energy, at the end of the day, is not so hard to discretize. Sort of the intuition here is that one thing I can do is if I have, for example, a vertex U on the source mesh and I want to discretize the Dirichlet energy in the neighborhood of U, I can look at all the outgoing edges from U, kind of map them maybe to geodesic curves on the target surface, which are expensive to compute, but computable. And somehow, really, what the Dirichlet energy is measuring is like the average length of that set of geodesic curves out from phi 1, 2 of U. So all of you guys, having taken 6838 for quite a while now, could probably cook up some version of a discretized version of, I think you got to all cook up a discretization of the Dirichlet energy that we wrote down, at least as I gave it to you. What we're going to see is just that it's a bit tricky to optimize. And it's tricky to optimize for two reasons. One is a little bit subtle and comes from differential geometry. We're going to push that back for now. But there's actually another one that I think is a little clearer from the perspective of 6838. And that's sort of illustrated here. Now, when I'm optimizing for a map from a surface into the plane, what are my variables? They're positions x, y in the plane. And no matter where I move my points, they're still in the plane. I don't have to worry about adding a constraint. Here, if I'm looking for a mapping from M1 into M2, well, what are my variables exactly? It's actually a little bit tricky to express this, right? Because, for example, one naive thing I could do would be to say for every vertex on M1, a mapping is just a position x, y, z on M2. But then I have a really tough constraint that I have to enforce, right? Which is that most positions in 3D are not on M2. So I need a constraint that my mapping doesn't leave that target surface. So rather than doing that, what Danielle proposed, which is a clever idea and one that I think is quite useful, is to work with something that she called precise maps. The basic idea here is rather than just having coordinates for every vertex I in the target, we're going to instead use barycentric coordinates along triangles of M2. So the basic point here is that I can think of a map as a matrix where every row of my matrix is a different vertex of M1. And then every row is essentially a set of coordinates on M2, which are non-zero on at most 3 columns. And those 3 columns correspond to 3 vertices, like this ijk that you see on the right-hand side of our mesh. And essentially, the coordinates sum up to 1, or just barycentric coordinates inside of that target triangle. And so this is going to be our space of maps, is a space of matrices that are non-negative, whose rows sum to 1, and where every row has at most 3 non-zeros, and those 3 non-zeros correspond to a triangle on M2. We'll call that the set of precise maps. And that sounds complicated, but really it's just keeping track of points inside of triangles on our target model. Okay, so at the end of the day, for example, if I wanted the coordinates that get mapped from vertex I on M1 to some point on M2, what would I do? Well, basically, I would just take the weighted average of like Vi, Vj, and Vk on the right-hand side, where the weights come from our matrix P12, which you can write as a matrix vector product as given on the slide here. So this actually gives a really nice discretization of the Dirichlet energy, where if we make a admittedly bad approximation, which is that distances along the surface are approximated by Euclidean distances in 3D, that should be like alarm bells in your head that like something has gone a little wrong. Then essentially we can write the Dirichlet energy as a weighted L2 norm on that matrix P12. So somehow now the objective function isn't so hard to work with, but we have really tough constraints, right? Because P12 isn't just a general matrix or even a singly stochastic matrix. It's a matrix with this funny constraint that at most there are 3 non-zeros in every row, and only those 3 non-zeros have to correspond to a triangle on the target mesh. So essentially we needed to do a lot of kind of tricky optimization and rephrasing of our problem in order to make this problem tractable or even kind of make sense. One aside, which I think was a clever trick, it was borrowed from a paper called Barycentric Coordinates on Surfaces from Daniele Pinozzo and company at NYU, is that this approximation of using Euclidean distances for distances along the surface is a pretty bad one. One clever idea was to take the original surface and embed it into a higher dimensional space where actually the extrinsic distances do resemble geodesic distances a little bit better. Essentially, this is borrowing some ideas from our metric embedding lectures long ago in 6838. And then it turns out that this quadratic approximation really isn't so bad. So I'll let you guys read up in the paper for details there, but it was a clever kind of engineering trick. So I mentioned that there are 2 problems with Dirichlet energy. One is that the target of our map is a little hard to work with, but we're going to cope with that by working in the space of these precise mappings. The other issue is a little more subtle. So here's a sort of an extreme version of the issue. So let's say that I'm mapping from this extremely coarse mesh, M1, into a dense mesh, actually of the same sphere, M2, and I optimize the Dirichlet energy. Now, here's the basic issue. The way that we've discretized the Dirichlet energy, it kind of doesn't know what happens in between the edges of M1, like in the interiors of the triangles here. And so, in fact, a really weird thing can happen, which is illustrated in this slide, which is that since our energy is basically just summing up over the edges and can't enforce bijectivity of the map directly, you can think of the triangle. So our mapping is kind of taking M1 and stretching it over M2. And you can think of what's going on in the figure here as the following, that sort of M1 is like a fishnet and is slipping over M2 and then just collapsing to a point on the other side. Right? And that's because our energy doesn't account for what happens in the interiors of the triangles. And the energy doesn't particularly care if my mapping is bijective or not. Incidentally, this turns out to be an issue not just in the discretization, which is the way we've illustrated it here, but actually with harmonic mapping more generally. So remember that we have this mapping phi 1, 2, which is going from surface M1 into surface M2. And we've written the Dirichlet energy E of phi 1, 2 as the integral of d phi 1, 2 squared dA, where this is an integral over m1. Incidentally, another thing that might be kind of raising your alarm bells is simply the fact that this energy is like not reversible, right? If I have a map from surface 2 back into surface 1 that I get from like inverting a map here, the energy will change. But in any event, one thing that you could do, which hopefully you all are trained to do in this course by now, would be to like take the first variation of this objective function in phi and then do some kind of gradient flow approach to reduce phi. Right? So what would that look like? That would be kind of like slipping around these points on M2 to reduce the Dirichlet energy. Now, it turns out that the theory of harmonic mappings, like of local optima of this objective function, go back to the 1960s and not earlier. And the first question that you might ask is, given M1 and M2, and given an initial map phi1, 2, what happens if I basically do gradient descent on this objective function, right? So I try to reduce the distortion of some initial map. So like I take my original domain, I wrap it over the other domain, but then I kind of let it relax by reducing this Dirichlet energy. Notice that in that smooth case, this kind of funny picture that I've drawn on the slide can't happen because I can't leave the homotopy class of my original mapping. That is to say that like if my mapping originally covers the entire target surface, if I just do a smooth procedure, like optimizing the position of every point mapped onto the other domain, I can never create a tear in my mapping or discontinuity. But it's not clear that that gradient descent procedure, like interpreted as a partial differential equation, has to converge to anything interesting. And in fact, I believe it goes back to the 1960s. There were two mathematicians, Eales and Sampson. I believe there's a P, but I can't remember. Who studied the existence of harmonic mapping, which is like a local optima or a critical point of this energy E. And so they actually studied it using exactly that gradient descent procedure, or in their case, what you would call it is gradient flow, because of course they have an infinite dimensional variable, which is this entire mapping. And essentially, what they showed is that so long as our target, and by the way, this works for higher dimensional manifolds too, not just surfaces, their theorem says that if M2 has a non-positive curvature, like it's a saddle, then this thing, gradient descent, converges to a harmonic map. And okay, why is this interesting? So essentially what they showed, and of course I'm oversimplifying quite a bit, is that in every homotopy class of maps from M1 to M2, there exists a harmonic map which can be obtained by doing this gradient flow, so long as M2 has negative curvature, and under a lot of conditions that I haven't written down. Unfortunately, when M2 has positive curvature, even just in some isolated place, things can go wrong. In particular, otherwise, you can end up with an artifact known as bubbling, where essentially now the mapping can develop singularities. So as I do my gradient flow on this Dirichlet energy, things can bunch up and cause singular points and all kinds of yucky things. So I'm looking at it now. I don't think maybe there's not a P. I don't remember. Question mark. I'll let you Google it. In any event, this basic theory sort of tells us that generically we shouldn't expect these kinds of algorithms to work, even if we could fix this fishnet phenomenon. And there are a lot of different ways to understand what goes wrong. One of them, from my perspective, is that the Dirichlet energy just really isn't the right thing to optimize here. It turns out to be okay for surface parametrization, but really this wants d phi to equal 0. But really what we want in these kinds of applications is for d phi to equal some kind of a rotation matrix, right? We don't want the surface to collapse. We want it to move rigidly. And so you can kind of understand the rest of this paper as somehow repairing the Dirichlet energy. So what we're going to do is add some objective terms to this original problem. Specifically, we're going to add a second mapping variable, which is the inverse, and add the Dirichlet energy of phi to 1. And essentially, by putting all of that together, we're no longer computing harmonic maps, right? Because we have a new objective function with more terms in it. But we're solving a problem which appears to be well posed. Now, I've been careful to use the phrase appears to be because we have not proven that carefully, but at least it overcomes some of the challenges like what you see on the slide here, where your mapping collapses, and it's no longer clear that this bubbling phenomenon is an issue. Okay, so let's talk about how we accomplish fixing some of these problems that I've mentioned. In particular, what we're going to do is add what we call a reversibility term, which is basically going to be the Dirichlet energy of the mapping going in the other direction. And that's going to prevent our map from collapsing, similar to what we saw in that previous slide. So in the continuous setting, this is easy enough. So we'll have a map 1, 2 and another map 2, 1. And we're just going to add the objective functions together as well as a constraint that they kind of compose the identity matrix. And essentially what this reversibility term does is promotes injectivity and surjectivity of our map, which is preventing that case where everything just collapses to a point, and turns out to help us with some of the discretization issues as well. In the discrete setting, in some senses, really isn't so bad. So we're going to add a new variable p21, which is the mapping in the other direction. And so in addition to our Dirichlet energy terms, our reversibility term here is going to compose the forward and reverse maps, p21 and p12, and ask that we get the identity. And so one way we can do that is expressed on the slide here, where we're just going to take the coordinates from the original surface, map them to the target surface, and map them back. And what we hope is that that's basically the same as the coordinates we started with. So if we subtract those, we should get something close to 0. So that's how we're going to try and make our mapping bijective. We're going to have Dirichlet energy, forward and backward, plus reversibility, which is basically just making sure that if I map coordinates to the target and back, I get what I started with. And that's basically going to be our target for optimization. It looks something like this. Right? So we have a coefficient alpha in front of the Dirichlet terms, plus a coefficient 1 minus alpha in front of the reversibility term, controlling the trade-off. I think in practice we find that alpha doesn't have a huge effect, which is a good thing. We don't want to go totally crazy here. So we know how to write down our problem, but optimization is really tricky. And the reason that it's so tricky is that these matrices P have this weird constraint that they're in the space of precise maps. Right? These singly stochastic matrices with at most 3 non-zeros per row corresponding to a triangle of the respective target mesh. And so the basic observation here is that what we do know how to optimize are functions of the form that I've given on the slide here. And you might not realize this, but essentially this particular least squares problem, even when S is a set of precise maps, is actually quite simple to solve. It basically boils down to saying, well, P12 times A is a weighted average of the elements of A inside of at most one triangle. So really what's going on in this problem is to compute every row of P12, it's just a loop over the triangles of our source surface. I'll let you guys convince yourselves of that at home. So at the end of the day, the optimization algorithm is going to try and leverage this particular fact that if we constrain to, if we put different constraints on P12, then really our problem isn't so hard. Incidentally, I forgot we put in the slides a little bit more details here to help you understand why this problem is solvable. So for instance, let's say that P12 isn't one of these precise maps, but just takes vertices to vertices, like this is a permutation. Then notice that basically all P12 is doing is just kind of picking out different, I guess in this case, columns of A. And so, right, we can basically optimize this thing by just finding good matches from one domain to another. I think I'm going to skip this because you guys are all perfectly well equipped to solve this problem. When you move to the space of precise maps, you need to basically extend that combinatorial argument ever so slightly to include triangles. Okay. Now, if you're willing to believe that we can solve least squares problems in the form like P12 times a matrix minus another matrix, that makes some sense, but it actually still doesn't solve our problem completely thanks to that reversibility term, which has products of these precise matrices, like what you see in the second equation here. So in order to fix that issue, we use a technique called half-quadratic splitting, where essentially we're going to introduce a new variable for the product p12x2, which is bracketed here. And by doing so, now, well, what do we have? We have p21 times that new variable minus x2. So if we freeze that new variable, then our optimization problem becomes feasible. So to add a little more detail here, well, we're going to add a new variable like x12 and x21, which are exactly the definition that I mentioned before. And essentially, we're going to just make that substitution anytime when our optimization problem is hard to solve. And so that leads us to three objective terms now. Now, the first two are what we had before, Dirichlet energy and reversibility, but notice now the reversibility looks like a least squares problem because we sort of factored the p12 and p21 terms, respectively, into x12 and x21. And then we had a third objective term, which is going to enforce the constraint that like p12x2 equals x12 in a soft way. So we'll just add e sub q with a big coefficient in front of it. You could probably write down a version of this with a hard constraint, but we didn't find it to be necessary. So this is our whole objective function in one giant pile here. You can see that this is a big engineering problem. So essentially, the first term is trying to make the geometry get mapped in a reasonable fashion. The second one is trying to make our map look bijective. And the third one is just enforcing a constraint in a soft way. So probably that coefficient beta is fairly large. And how do we optimize this? Well, essentially, we alternate between different sets of variables. Now, if I optimize for the p's with the x's fixed, it becomes one of those least squares problems that's just equivalent to looping over the triangles. And now if I optimize for the x's with the p's fixed, that becomes just a least squares problem that I can solve using a linear algebra library. So at the end of the day, this alternating algorithm actually does reduce the objective function in every step. You could probably convince yourself that it actually converges. I'd have to think about that one a little bit. And what we find is that it gives us really nice mappings. So for example, here we're comparing to a few different techniques. So here there's a source mesh and a target mesh. And as with the visualizations we saw in the last lecture, we just take a texture, in this case of these digits, and map it from one onto the other. And here you can see that the mapping that our system, this reversible Dirichlet energy optimizes gives really nice mapping, even between these quite different domains, which is pretty exciting. And in fact, if you compare to some of the other past work, for example, this hyperbolic orbifold, which co-parametrizes into hyperbolic space, you'll see the distortion is a lot larger, right, if you look at that bird on the top. Similarly, here's another comparison. You can see that this symmetric Dirichlet energy creates nice smooth mappings from one domain to another. And one of the really fun things that we see is that this algorithm actually gets used. So in any event, hopefully you guys have some intuition for what it takes to engineer a system for smooth mapping from one triangulated surface into another. And I think this paper basically exemplifies the many challenges that arise in this area. One of the challenges is how do you represent your map? For example, here we decided to represent maps using this precise maps concept. But even there, computing some things like the smoothness energy become quite difficult, right? Because essentially, it's very easy to deal with maps into Euclidean space, but when you map into curved surfaces that are discretized using triangles, then computing things like the Jacobian of your map becomes actually quite difficult to approximate in practice. Moreover, a different challenge that we had to face was the fact that not all objective functions are actually well posed for mapping from one surface into another, rather than mapping into Euclidean space. So I briefly mentioned this Eales and Sampson theorem, but this is actually a really critical issue. That, for instance, doing gradient descent on Dirichlet energy really doesn't make sense when your mapping is into a target with potentially non-negative curvature. So we had to revise the objective functions that are popular in differential geometry theory to fit the application we care about. Then finally, from an optimization perspective, we have this really yucky constraint, which is that I have a mapping from one surface into another. So I need a constraint, which is that my map doesn't leave that target surface. We coped with that by introducing these precise maps and then using half-quadratic splitting to cope with that constraint in an efficient fashion rather than having to do some crazy projection or something like that. Now, this isn't to say that this algorithm is the end of the story. I think there's still a lot of problems to be solved, everything from map representation. For example, we didn't really tackle the problem of what goes on in the interiors of triangles, to thinking really carefully about different distortion energies that can measure properties of map from one surface into another. But I think this is a great paper to just get some feel for the types of challenges that we face. So I encourage you to give it a read. And of course, come talk to me about it, because this happens to be a paper I know quite a bit about. So with that, this is just a fun extra lecture segment that you can watch optionally if you like. And with that, I will see you next time to discuss consistent mappings, where we're going to see that reversibility term in this paper actually takes on a whole new light in the world of cycle consistency. So with that, I'll see you next time.